So something happens to the civilization, and it disappears. Um, so I am getting this record message on my.
Yeah, sorry, that was me, Nitin. I forgot to start pressing.
Okay. um, so yeah, so this is what motivated me. Now I come from the part of the world where this civilization, existed. So let me show you some maps of what I am really talking about. So here is the map um, of the mature phase when this civilization was at its height. And these, if you see, there are some of these dots here, and these dots represents different archaeological sites that archaeologists have found. And these sites belong to the mature phase, and they are somewhere between 4,600 to 3,900 before present. Okay, so I've changed my time units. Now I will be talking in the units that people from climate like using. And this civilization during this phase was in terms of its spatial extension was gigantic. It was even, some estimates say, probably was even bigger than the Mesopotamia and ancient Egypt, at least in terms of its spatial expansions. Its population is estimated at during this period around maybe 5 million or something. So these cities that you are seeing, especially this Harappa and Mohenjo-daro, they were like New Yorks and Tokyos of that era of the Bronze Age. And you can see that there's several countries that it covered. Most of the sites are in modern day Pakistan. There are some even in Afghanistan, and there are a lot of sites in India, in northern India. So as we go along in the time, what archaeologists found, that they found fewer and fewer archaeological sites. Yeah. So their estimate is that somewhere around 1900 BC, that is 3,900 before present, this civilization started to decline. And by roughly 1700 BC, that is 3,700 years before present, many of these cities were abandoned. So if you look at the map, this is what was happening. That you have fewer and fewer cities, and then finally, in the post-Harappan phase, you don't have that many sites remaining. So this civilization gets its name Harappa because of this town up there in this town here, and this is the town which remained until this last map. In this map, this is the map in which this town disappears, and that's why this phase is called post-Harappan phase. It was one of the bigger towns of the civilization. So now, what happened between 3,900 to 3,600 before present? I mean, this is, of course, an important question, because this is one of the significant human civilization that ever existed on the planet, and what went wrong with it, that it disappeared. And it's of interest to people from many different disciplines, not just archaeology, anthropology, and history. People in climate and in sociology and things like that, they're also interested in this question. This civilization is also known for many achievements, like their towns were pretty advanced. They were the first ones who were using town planning. They devised very complicated ways of measuring things, and they also had trade relationship with Mesopotamia, and so on. So now there are three different theories that what possibly happened to this civilization, and why did it decline, and why did we don't see any other civilization coming up in this region until very late. Yeah. So so what really went wrong there? So the first theory is invasion by Indo-Aryans. Wherever there is a word Aryan, that's a problematic theory, but that's what one of the theories is. Indo-Aryans were nomadic tribes from Central Asia. It does seem that they did come into the Indian subcontinent, but there is not much archaeological proof that they destroyed this civilization. However, this theory stays that Indo-Aryans invaded and destroyed this civilization, and why this theory um, is not very well accepted, and is the fact that when you go and do archaeological research in this area, you don't find signs of violence. If these invaders came in, they must have killed people. You should find a lot of skeletons with injuries. You should find burned towns and cities, and there are not much in terms of these kind of evidence to support this theory. But there is a section of archaeologists who continue to pursue this. So this is the first theory. The second one, which has quite a bit of support, is earthquakes. So if you look at this region, this whole region is placed in what we call a tectonically active area. There is active tectonics in this region, because you can see that it is Himalayas are there. Himalayas are very active tectonic wise. So and there are some evidence now that there were earthquakes during this period in this region. However, these earthquakes could not have destroyed a civilization which was of this size. Yeah, it doesn't seem plausible. There's something else should have happened. You know, earthquakes could be the compounding factor, but they did not give the, what we call the final blow to this civilization. There is something else which we don't know, or which probably we know, we don't want to accept it. And that third reason is climate change. And there is a lot of work which shows that perhaps it was climate change which brought end of this civilization. The climate change theory states that there was a big aridification event, and because of that aridification event, the rain-fed rivers that were there in this region, which were the main supply of fresh water to the inhabitants of this civilization, they dried up, and because of their drying, it became harder for such a large civilization to work. So most people migrated towards other regions of South Asia where the water supply was better, and yeah. Now, this third theory of climate change is very plausible. So we have to look, and to understand it, we will have to look into the climate of this region. So this region, and this is the map of modern rainfall, summer monsoon rainfall. Monsoon plays a very important role in this part of the world. Because it brings, it's the main source of fresh water supply to the inhabitants of this region. And of course, we know that during the period where, in the civilization existed, monsoon must have played an important and critical role in sustaining that civilization. One can say that, hey, there is a big river that flows through this. There are these huge rivers, glacier-fed rivers that flow in this region, and aridification should not have that big of a effect. But the problem is that most of these sites that I was showing you were not found along these glacier-fed rivers, but they were found along rivers which were monsoon-fed, more shallow rivers. Perhaps technologically, at that point of time, humans were not so advanced that they can live along and survive along these gigantic glacier-fed rivers. Perhaps they were more closer to these shallower rivers which monsoon was feeding. So this is the third theory. Now we can actually test it. Yeah, it's not that hard. So to test it, we will have to go into paleoclimate. So there is this data set that came out in 2017 where they actually tried to study this civilizational evolution. And this data comes from these paleotherms, this calcite deposit that you found in caves. And one of the isotope that's found in these in these stalagmites, and this is the place where this data came from, the one that I'm talking here. Yeah. So this is the spot. Okay. Yeah. So one of these the metrics that they can give, that they can derive from these speleotherms is the content of delta O18, and this particular isotope seems to be correlated with the rainfall patterns. I mean, this is not a linear correlation, that but it does embed in it in its variation the hydroclimate of a particular region. So if you see that this star is very close, this spot is very close to where the civilization was growing. So perhaps this particular time series have the signatures of what happened to this particular civilization. Now, they, I mean, if you look at this paper from where this data set originally appeared, they did try to figure it out, but but generally paleoclimate data is quite complex. It's not that easy to apply statistical analysis on them and reach a conclusion. We really need to dig deep mathematically and statistically to find out exactly what's going on in this data. So their analysis was not that sophisticated, although their data is wonderful. There are very few time series which you get with this high resolution for this particular region. So that's a fantastic part of this paper. Now, so let's look at this time series. Now we can divide it into different phases. Yeah, phases based on what was happening to the civilization. You have the pre-Harappan phase. That's the phase before the civilization started. Then the early phase, the mature phase, and the late phase, and then the post-Harappan phase after the decline of the civilization. Now, if this climate change theory is correct, it will imply the following. It will imply that the monsoon has to change in some way, so that there could be an aridification of this region, or something else can happen, you know, for this region to become inhospitable to the point where a big civilization cannot sustain. So something should happen in this part of this time series, and that's what I wanted to test. Can we find something here? So this is just rephrasing what I'm saying, that if climate change caused the demise of the Indus Valley civilization, then monsoon dynamics should be different in these time periods. I mean, the time period covered by this here and this time period after that. Yeah. Okay, so there should be some difference between them. So let's try to build a mathematical framework to answer this question. What I'm trying to do is not unique. People have tried to solve these kind of problems in all possible ways. People have thrown kitchen sink at this stuff because this is probably the most important kind of problems in paleoclimate, finding out where the climate has changed, where the regime shift has happened. So there is gigantic amount of literature available on it. When I was a PhD student, I also tried my luck with this, but I was not very successful. But this time I was totally thinking about something totally different, and so I will show you how I went about this time. So the idea is the following, that let's say this time series is, call it x of t. Now we know that when we model a complex dynamical system, most of the time we write a differential equation, x dot is equal to f of xt, and then there is some parameter gamma. This x, this big X is a vector that consists of, it's an m-dimensional vector. And often what will happen that your parameter will also evolve with time. In real world systems, your parameter usually tend to evolve with time, because if you look at monsoon, the main parameter is in what drives monsoon is the temperature. Yeah, temperature gradient between land and the sea, and this temperature gradient changes over time as the solar insolation changes, the ice cycle changes, the snow and content and things like that. So usually these parameters are time dependent. And so for a second, assume that this X represent one of these variables of this system, our observation. That's what we have. So this is the framework I have. And in our dynamical system classes, we learn this kind of framework all the time. So I can take an example from dynamical system and I can actually create something like this. So I decided to create an artificial example for this situation. So what I did, I took one of the simplest nonlinear system, 3D nonlinear system I know, the Rosler system. And I took a case where this parameter A, so this is a three-dimensional system, X, Y, and Z. And this parameter A, if it's changed between 0.32 and 0.38, it creates two different kinds of dynamics. I mean, we have a lot of examples I could have taken to create two different dynamics for by changing a parameter, but this is a very, very interesting case. Here, the change in the dynamics is very, very subtle. Yeah, they almost look the same. So one of them is called the spiral type chaos, and another one is called the screw type chaos. And as you vary this parameter, it goes between these states. So what you can do next is, now I take away all the other information and I just pick one of these three time series. Yeah. So what I do is that I say, hey, I won't tell you that there was a Y there was a X in this system, there was a Y, there was a Z in this system, and there was a parameter A in this system. You know nothing. You just have one of the variables Y. Okay. And now, if I give you this, can you do the following? One, can you identify the transition points in this time series where the transition happened between these two different kind of chaos? And more interestingly, and the thing that I was really interested in when I started working on this problem was, can you cluster the dynamics into groups? Yeah, into two groups here. We all time in data science, we talk about clustering, and everything is being clustered. But you don't see that much of clustering being applied to dynamics, clustering things into groups. So can you apply some kind of cluster analysis to it? And a bonus thing, hey, can you also reconstruct the underlying parameter? Perhaps in this case, because this is a very, very simple system, you might be able to reconstruct it. But the main thing is 1 and 2. If I can do 1 and 2, then I can actually find out, I can actually tell you what happened to the monsoon during that phase. So now I said, okay, let's do this. Then what I did was the following. I devised a method, or I combined several different methods into one coherent thing, yeah, one coherent hybrid piece. Now you might say, hey, we can probably do it in fewer steps. Why there are these 4 steps? So I need to warn you that paleoclimate data is usually very, very challenging. So you need something really sophisticated to figure out things in that. It's usually very short. It has noise in it. It has uncertainty in it. It has everything, every sin that a data can commit will be there in paleoclimate data. So you need something more serious than any simple statistical approach of finding out variability or trends and things like that, or just using a recurrence plot. Okay, so it has 4 steps. The first step is a time delay embedding. Okay, because I want to think about this system as from the perspective of dynamical system. Then I use recurrence plot, and there is a simple reason for using recurrence plot. Recurrence plot is one of the only tool from nonlinear time series analysis which has shown consistent success in analyzing these paleoclimate time series. It seems to be more robust against all the bad things that exist in paleoclimate data, like noise and shortness of the data and things like that. Then my dream was to cluster the dynamics, and if you look at machine learning literature, clustering the dynamics or dimensional reduction, these kind of problems these days are solved using manifold learning. And one of the really famous method within manifold learning is Laplacian eigenmaps, which is also supposed to be very robust against presence of noise in the data. And the fourth one is a estimate of dynamical complexity called Fisher information. Ecologists use this metric, and this is very, very popular metric. However, it's more suited when you have a very long time series. The kind of time series you get in paleoclimate, it's slightly less appropriate. But if you do for the steps 1, 2, 3, I can turn the data into a format where Fisher information will work really well on it. So let's start. So step one. So step one is time delay embedding, that you take, you build these vectors, time delayed vectors from your scalar observation like this. This guy M here is the dimension, embedding dimension, and this tau is the delay. And there are many different ways of estimating these things. When you choose M, you have to choose M according to these great guys here, Takens, Whitney, and others. They suggested that, hey, choose this M to be greater than 2 times of the fractal dimension. So, and if you do that, magically you can reconstruct the attractor, the thing that I was showing you earlier. Now, there is an issue with this stuff though. All this it doesn't work for the kind of system I am talking about. So I said that my gamma is time varying, gamma is a function of time, the parameters involved in it. And these theorems are not valid for these non-autonomous systems. But there is a technique that you can apply to these systems as well. And this technique is not based on any theorem. It's just based on numerical observations and some heuristic arguments. And this seems to work. I have tried it, and it seems to be something that works. This paper by Kahns and Hager talks about non-stationarity, how you can use over embedding and deal with non-stationarity in a time series. So the idea here is that you take, this is the fractal dimension plus the number of parameters you have, and you multiply that by 2, and that's what you choose your embedding dimension. So way higher than what is recommended by these theorems based on Takens and Whitney's ideas. So this is going to be my technique for embedding it. Now, after I embed the vector, I construct a recurrence plot, which is very simple to construct. Recurrence plot, you compare 2 time delayed vectors, yi and yj, and you try to look at whether they fall within an epsilon neighborhood. If they fall within the neighborhood, you put a 1 in the matrix, rij. If they are outside, then you put a 0. So what will happen is that your time series will turn into this kind of a matrix, yeah, where these orange dots are ones, and then you have zeros. Okay, this is step number 2, making the recurrence plot. Step number 3 is this Laplacian eigenmaps. Now, what Laplacian eigenmaps does is that they give an embedding map by using the eigenvectors of the graph Laplacian. Now you might say, where is the graph? So this recurrence plot is a graph, yeah, because it has zeros and ones. You can treat a recurrence plot as an adjacency matrix of a graph. And recurrence networks, the method of recurrence network, that's what it does. It does treat that as a graph. So if you're treating as a graph, you can find the graph Laplacian, which is just simply d minus w, where w is the weight matrix. I will come in a second how to find w, and then d is the diagonal weight matrix. Now there are different choices for choosing this weight matrix. There is this one, which is called Gaussian kernel. We don't need actually this version of the weight matrix. we can actually use the second option. So there are several different options how you can construct a weight matrix. If you have static data, you can use this Gaussian kernel, trying to find out distances between points and things like that. But we don't need to do all that jugglery. We have something very simple. We already have a matrix which can be treated as weight matrix, the recurrence plot. Yeah. So we just set this Wij is equal to Rij, and boom, we have a weight matrix, and then we can calculate the graph Laplacian. Boom. And if we can calculate the Laplacian L, then we can have its eigenvectors, we can have its eigenvalues. We know that this lambda naught is 0. It's all its eigenvalues are contains 1. All the elements are ones. So we discard this particular eigenvalue and this eigenvalue and the corresponding eigenvector, and we take all the other eigenvalues. And now what we do is that we use the eigenvectors coming from the graph Laplacian, and we embed our time points in this new embedding given by these eigenvectors of the Laplacian. So yeah, so that's what it does. So your y. So what I did was that I had this y. I scalar data, I converted into a time delay embedding. Then from time delay embedding, I put it into a recurrence plot. And from recurrence plot, I'm doing this. And you will see that this will be able to cluster the dynamics. It can do the magic, what we want to do. Okay, this is just giving the same information again. Anyways, so if you do that, your data will turn into something like this. So what I'm doing is that I'm plotting just 2 dimensions of these eigenvectors, yeah, and you get a heart. So this is a good good going. Rarely you see while analyzing data, a heart will appear. So this is some interesting signature that I'm going in the right direction. All right, now what you can do with this heart. This is not clustering the dynamics into anything. If I color it with time, I still don't see any clustering of the dynamics. But I know, and I have visualized it in different ways, that the clustering is there in this picture, but I just can't see it because I need one more thing, some quantity that will remain constant or that will be invariant on one geometric shape or one of these manifolds, some quantity like that. If I can have that quantity, then I can see the clustering. Okay, but before I do that, before I do another round of jugglery, I just want to summarize with that what I really did until now. So I had a time series. In the first step, I did time delay embedding. Then I constructed a recurrence plot, and from recurrence plot, I got these Laplacian eigenmaps, and I'm plotting here 2 of its dimensions. And now I want to do something about this heart, because this heart has the information that I need hidden in it. So I need to do one more thing with it. And that I do using another metric called Fisher information. Fisher information this is a wonderful metric, yeah, and I think it can identify dynamical regimes in most cases, and it's developed by I mean, the Fisher information was given by Fisher, but the version that you can apply to the time series analysis is given by these guys, Mayer and Pawlowski, Cabezas, these guys. So if you look at the integral at the top, it measures the amount of information about the unknown parameter theta that's contained in the random variable x. The issue is that this integral looks really pretty, and if an integral looks pretty, that means it will not be useful generally. So we have to do something about it. And by the way, you cannot calculate this integral. There is no way I can calculate it from my data. There are actually different interpretation of these integrals, but one of the ones that I will be using is the fact that the information about this parameter theta is contained in this observable, and that's what it's measuring. Yeah, how much information about theta is there in the observable. So what these guys did, they did some magic with this metric and changed it into a form where you can apply it to time series analysis. One of the things they did, in place of having this conditional probability, they introduced this guy P of S. Yeah. And this P of S is the probability of observing different states of the system. And this Q square X is just this Q of S is just the square root of P of S. So now, and now you can define states as the different segments of a trajectory or of an orbit. And that's what they did. But I'm not going to use that framework. I will do something more with it. Then they went on. If you look at these papers, there are these long calculations, which ultimately lead to a discrete version of this metric. And this discrete version looks like the one that I have in orange here, this one. This is calculatable on a time series. So these QRs are the probabilities of points being in a certain state. Okay, so I will work with this discrete version, and then we see where we go with it. So let's say you define a state as, you know, so for example, any point in now you have an embedding for it in terms of these Laplacian eigenmaps. What you can do is you can describe an state as to be this hyper rectangle that you're seeing here, and with some uncertainty delta qk, yeah, which is in dimension k, and then what you try to observe is you try to count how many points fall within this hyper rectangle. If 2 points j and I are within this hyper rectangle, then they are in the same state. Okay, and then there are tricks to how to set this uncertainty. There are several different ways of doing it, but that's not very important for us. So now if you can make these little boxes, yeah, and you can start populating them, then you can find PR, which will be how many points are in state R, which is the box R, to the total number of points that you have. That will give you PR, and then the square root of that will give you QR, and then you can calculate your Fisher information. So in their case, the state was these segments of the trajectories of the orbits, and in my case, these states are parts of or pieces of these manifolds that I have constructed. Some region of this manifold. Now, you will not take the raw values of this metric Fi. You will average it over a certain window, and once you will average it, you will this guy converges really fast, so it becomes kind of a constant. So it will give you a number, one specific number for different windows that you take. Now, so we have all the machinery that we needed. Now let's apply it to the time series that I had. And boom, this is what happens. I can see that the jump in this Fisher information corresponds to the exactly to the points where I have added the artificial transitions. And I built this statistical test, which is just, you know, bootstrapping the Fi values, creating several different samples of them and calculating a value and putting the 90% confidence band of that as this statistical band. So the bottom line here is that, relatively speaking, two things which are above and below this above and below this band have some probability of being coming from different dynamics. That's what it means. Now, the thing that I was looking for, can I cluster the dynamics? And yes, I can do that. So these are the manifolds, and now this is plotted versus those two dimensions plotted versus the Fisher information. And you can see that there are two shapes in it. One, this heart-looking shape, and the another one is this more fuzzy kind of of shapes, and this one of them is the spiral and the screw type chaos. So that's, you can cluster it. Okay, but this example was very simple. Let's make it a little complicated. Let's have a little more fun with this thing. And one thing that you can do is that you can start varying your parameter more slowly, more continuously. In place of having abrupt transition, you have more continuous transitions. Yeah, at some point it crosses the threshold value. The A crosses the threshold value. Can this method still identify these transitions? And it seems it can. It can pick up where your parameter is crossing the threshold. It can again show you that there are two things in it. It doesn't tell you which is what, but it does tell you that there are two kinds of dynamics in it, because it has these two distinct looking shapes. There was a bonus thing I was looking for. Maybe, I can construct the parameter itself, the parameter variation itself. So you take this Fisher information and you smoothen this. In place of taking the average, you smoothen this Fisher information. And if you do that, you will see that it kind of captures the variation of the parameter. This stuff is not in my paper because there are issues with it. But the one issue is that when you talk about monsoon might have multiple parameters in it, not just one. So I still don't know how to get situations, how to solve a situation where multiple parameters are varying in the system, and then able to reconstruct that. So that will be more appropriate scenario for climate. But I can do this much. That much I know, that I can get at least one parameter. You can make it even harder. Your example, you can add noise to it. Let's say you add 30% noise. Yeah. Will it still pick up the transition? And it seems like it still can get you the transition. So it can still show you that you have two things hidden in it, and there is a transition happening. You can try some other funky things. You can just remove 60% of the values from the time series and ask it, hey, can there are two transitions, can you show me again? And it can still do that. It can still show you the transitions wherever they have happened. And it can also show you, even in this case, when you have removed 60% of the values, that you have two structures in it, two different kinds of dynamics in it. So it seems like this technique works, and it's pretty robust. I have never seen anything that works so well. In these situations, I've tried to develop a lot of different kind of things with recurrence plot, but rarely I have seen an example where I can remove 60% of the values and still it can show me the transitions. So this seems to work fine. So now I go back to my original motivation, why I was doing all this jugglery. And my original motivation was that what happens to the monsoon. So let's go into that. So something should happen here in the late phase, yeah. So I ran this algorithm on it, and what it shows is that indeed there seems to be a transition during the late phase in this time series. And also there was one more transition, which I'm little skeptical about, but there is a transition right when the Harappan civilization, this civilization started in the early phase of in the early phase of the civilization. So what really happens is that if you plot those manifolds, you can clearly see that monsoon during the development and maturing of the Indus Valley civilization was living on this manifold, on this shape. And in recent time, monsoon is living on this butterfly kind of a thing. Yeah. And there is this little thing that probably belongs to this butterfly, but it's before the early phase of monsoon. Now, perhaps what's happening here is, and I think we also know that monsoon generally have two states, yeah, and it tends to jump between these states. So this is what's going on. That around when this civilization was taking off, monsoon was in a state where a lot of rainfall, it is quite intense, and a lot of rainfall happens in in deep into the northern parts of the Indian subcontinent. And then it came back to its usual state, which we are still observing, where that region is more or less arid, and we have more rainfall fall over the southern parts. So this is what it seems to be going on. I have a lot more intuitive understanding of this thing because I've worked a lot on monsoon. So this is very much feasible that that's what's going on. We still need to figure out that what causes these transitions, but at least we know that there is something with monsoon that has happened around that time. But what caused it will need a little more work. So in summary, what I was showing you is that if you integrate methods from what all is going in machine learning with dynamical system, they at times can lead to powerful tools for the analysis of complex system, as we are seeing here that it works so well with paleoclimate data. Michael, is my time up? If not, I can give you one more story.
Oh, we could take one more story. We've got a few minutes.
Okay. All right, so let's do one more story after this. Yeah, that's why I kept it. This is the new thing I was looking at, and I thought because you guys are in Australia, probably this will be of some interest. So there is this phenomena that happens in the Indian Ocean called the Indian Ocean dipole, and it is these irregular oscillations which leads to warming of the eastern part when this dipole is in its positive phase, and the cooling of the western part. And when these oscillations happens of heating and cooling, the rain patterns over this region changes. And I think there is some influence of this system even on Australia and Australian monsoon. But we were very sure that over Africa, over India, and over Southeast Asia, the rainfall pattern tends to change. So, for example, you can see that when it's in negative phase, there is big drought over Africa and Middle East and India. This is quite a recent discovery. People didn't know about this phenomena. Now, what happened that recently there is this another data set that came up, and this is a paleoclimate data reconstructed from these oral records. And what they have done, they have taken these spots, which I'm showing here, these places, and they have constructed a paleo index for this phenomena, these oscillations. And this is how their time series looks like. Their index for these oscillations. And their claim is that in the later half of this time series, in this period, the intensity and frequency of these events has increased, due to which rainfall patterns over this large part of the world has changed, Africa, India, and Southeast Asia, and places like that. So I thought, okay, let's take a look at this thing, what's going on here. Really, is there a different dynamics that's going on? And because this looked to me quite a simple system, because there are just these two oscillations, I thought probably, I might be able to find what is driving this change. So there is indeed, it seems like there is a transition around in the second half of this data, which actually is quite visible that, you have these bigger oscillations here, more intense oscillations in this part. Now, this is not that significant because the original publication did say that now we are observing more intense and frequent events of this phenomena, but they never talked about what is driving this change. What is it? Yeah. Generally, we know that these kind of things are. The obvious thing is to look at climate change, that perhaps is the global temperatures that are driving it. So what I did, I again took that smoothened version of this Fisher information, and then I said, okay, let's compare it with the global temperature records that we have, and will that capture this change in the Fisher information? And it seems like that if you put it on the same time scale, you use the same smoothing in the global temperatures, it seems to match the variation in Indian Ocean Dipole Index very well. It's actually pretty highly correlated. 0.96 is the correlation between these two things. So it seems like that this change is driven by increasing temperature of the planet. So yeah, this was my second story. This is an unpublished story. So I thought maybe I can share with you all that I'm still applying this this method to other data sets. So thank you very much. Thank you. This is all I have.
Thanks, Dishant. Do we have any questions from online? Yeah, who was that? Questions there?
Oh, may I?
Yeah, sure, go ahead.
The Indian Ocean Dipole is very interesting because that has quite a big effect on the climate of Western Australia, more than El Nino. And but we think that there are also some links between El Nino and the Indian Ocean Dipole. And I'm just wondering if it would be possible to use some of your methods to test those theories.
Yes. So yeah, Jennifer, thanks for the question. This is yeah, really interesting thing that you pointed out. So we are trying, I'm actually trying to do something like that. Yeah. Because what happens in the Pacific is influencing both monsoon and Indian Ocean Dipole, and then there are several other phenomena that are influenced by that. So when I was talking about monsoon, I still don't know what causes that transition. Yeah. For example, in Indian Ocean Dipole, I suspect that it is just what the trend we are seeing are just related to the changes in the global temperature. But I have no idea about monsoon. One of the hypotheses is that the monsoon changes are linked to the changes that happens in ENSO. And there's a recent paper where they have talked about volcanic forcing, being the intermediary which connects ENSO with monsoon and leads to transitions in monsoon. I don't know, but this is interesting to look at these time scales. How could we build these connections, these teleconnections that exist in modern climate? We know that how ENSO interacts with monsoon, or monsoon interacts with ENSO, and then what is the interaction between Indian Ocean Dipole and so there is a scope for developing these methods a little further, so that this kind of analysis can be done, that what is really causing these changes. Yeah. What are these teleconnections are? Some kind of correlation analysis, nonlinear correlation analysis, synchronization analysis like generalized synchronization and things like that. So this is something on I'm trying to work on these days. Yeah.
Oh, that's extremely interesting and promising. Thank you very much.
Yes, thank you.
Any other questions from online? Oh, Thomas is reaching to unmute himself. So what are you going to say?
So thank you for the talk. It was very interesting. When you find these transitions in your Indian monsoon site, over the time scale, can you actually guarantee that the source of your delta 018 is still the same? Because I mean, as soon as you have different kind of capture regions for your delta 018, you are in deep trouble.
This is from the same site. This is the same site.
But the question is, where does the delta 018 come from? Does that always come from the same site too? So
yes,
is it still the same kind of capture region in the ocean where you have your evaporation and that is driving?
I think this data set, the one that you're talking about, Indian monsoon one, is from the exactly same site, and I think it probably is from the same stalagmite, as far as I remember it. So this is, yeah. So the one big issue is that we do not have very high resolution and good data set from this time. Yeah, we do not have that, and from this region. Where the Indus Valley civilization grew, we do not have very good paleoclimate data. and I have looked into all the paleo records, and the best data that I could find was the one that I have analyzed. I have gone through a lot of pain and analyzing, I think, everything that exists on the Indus Valley in terms of paleo data, but none of them has this kind of resolution and quality. This is the best I have at the moment. That much that I'm quite confident about, that there is nothing better than this at this instance, and so close to the whole action of the civilization.
Yeah, of course.
Yeah.
But the other thing that I wonder is, I mean, when we are talking about the monsoon, the global monsoon is certainly a thing. So do you actually see something like synchronization of this major shift that you see around 3,600, 3,800 in other monsoon areas too? So I'm thinking about, I mean, the other one that comes to mind is there are data sets in China, there are data sets in Western Australia, which certainly couple to the Indian monsoon during that time. And so it would be interesting to actually see whether or not this transition that you find is also present in the closest or coupled monsoon systems that are around.
Yeah, you mean the data set that comes from Dongi Cave and things like that? Yeah.
Dongi Cave, KNI 51, these kind of systems, yeah.
Yeah, I have in the past analyzed those data set, but not recently with this method. Yeah, but I know that there is a coupling between these all these sub-monsoon systems that we have all over the world. So one thing we know that during this phase, there are several reported aridification events. So monsoon is not something, you know, it has been recorded in the Middle East that there was a big aridification event which put a lot of strain on Mesopotamia. Yeah. So there is some evidence that there are certain during this time period that I'm talking about, at many different spots on Earth, they have observed aridification events. Now, these two being important because there were these big civilization and they can see the influence of things, you know, of climate change. So yeah, so there is some evidence in that direction. It's not totally that. Yeah, and I'm forgetting the name of these events. You know, these events that happen over the Holocene period. Are they called Hendrix event or one of them? There is yeah. So these ones. So they are supposed to be the drivers of these aridification events, as the ice level changes in the North Atlantic. There is some relationship with that of these events. So that's one thing that people have worked on, but I haven't tried now because I'm still looking into. So one of the main things here is that what has caused these transitions. You know, for example, in case of Indian Ocean dipole, I know that it's perhaps the global temperatures. You know, that's the only driver. You know, it has a linear dependence on that, and as the temperature will increase, these oscillations are keep getting bigger and bigger. But I don't know about monsoon. That what is the driver of these transitions? Is these Henrich events that drives such transition, or is something else? It's something that happens in the tropical Pacific. Most probably something goes in tropical Pacific, because every time we see transition in monsoon, we find connections with the ENSO. So that's an open problem and something I'm very interested in and trying to figure out. Yeah. So if you have ideas, please feel free to share that. You know, if you know data set or that can be used to understand these teleconnections at the paleoclimate time scales.
I mean, it is pretty much a scary, complicated system in that sense that you have something like these big circulation patterns. And since we know so little about what was happening in the atmosphere, I'm not hopeful that we can actually reconstruct something like the cause unless we are running something like climate simulations under certain conditions and so on, and have a look in there.
There's conditions in the oceans that matter too.
Exactly,
so
yeah. But they might
an
be
extra complication.
like the Gulf Stream or something like this.
Exactly.
Cold surges and so on.
The Antarctic.
Yeah, exactly.
Circulation.
So this is exactly the problem that we are facing, that we know so little about the system. Because all this fine structure, and I'm talking about ocean circulations and so on, are not accessible to us.
Exactly.
Yeah, that's exactly, that's an issue. Yeah. We do have, but when my results have inspired the Indian Institute of Tropical Meteorology. There was a they want to run some Holocene simulations to see if they can generate such a transition.
Yeah.
So there are people who are interested in seeing that what I'm saying is correct, that it happens. So there are two pieces that they want to do. One, can they use all these transitions that I'm showing to validate their models, believing that my transitions are correct? And then believing their models, they can produce, so people are trying to do that, that they can reproduce these transitions in models. There is an effort in that direction as well. Yes, Michael, you wanted to ask something?
Yeah, so I just did a sort of half comment, half question. I haven't quite formulated it yet. I guess you started out talking about, before we get into the climate stuff, the underlying thing you were trying to test was whether there was a change in the dynamics.
Yes.
And all of the time series that you use, the toy ones as well as the climate ones, there's there is a change in amplitude in the data. There's a drift.
Yes, there is.
And so if we did like a moving average window just to estimate the distribution of data values, you would see a transition there. But this is just a transition this is just a change in the observation function.
Yeah.
So I wonder whether it's possible to somehow filter it to remove that first, to test whether or not what you're detecting is a change in the dynamics or just some artifact.
So one thing that I'm doing, that I'm resampling this time series.
Yep.
So I do linear interpolation and then resample it. But there are these artifacts of changing resolution at different places, but they are at each, somewhere there are some places where the resolution increases and there are some places where resolution decreases. So it's all at, it's quite everywhere in this time series.
Yeah. Okay. Any other questions from anyone else? If not, I should have made a special thank you to Nishant, because despite his background, I'm sure it's not sunny at the moment in Rochester. It's what, 11 p.m. now, or?
Yes, it's 11 p.m. Yeah.
So
so thank you very much for giving me this opportunity to talk about my work, and it's an ongoing work. I continue to work on these problems, and if you have ideas and inputs and comments, please feel free to reach out to me. And I've been trying to develop a lot of these methods which can do this kind of analysis for a while now. So yeah.
Thank you for the talk. It was really interesting.
Thank you, Michael.
Well, I had to get up out of bed.
Yeah, you had to get
holiday.
Bed at like 9:30 for this, so that was a bit.
Yeah, that was a little bit hard for me.
I'm sure you're actually out of bed, and you're not just sitting up.
No. So I'm. I can't.
So how many people? How many participants did we have for this meeting?
Not so many, because we usually have it at 3 in the afternoon here, which is 5 hours later. So I think we confused a few people. So we're around
Okay.
between the people in the room and the people online, probably about 15.
Awesome.
Yeah, there's
Yeah.
a few people that probably going to turn up for the seminar at 3 p.m. and wonder why no one else is here.
Yes, I had I have to teach in the morning, so that's the only business I have.
Yeah, no, that's okay. Completely understand. I've got a
So that's why I said I could I'm somebody